In the fifth part of this unit, Unit 8, we will look at min-max lower bound for statistical estimation. And this is a very interesting topic. Unfortunately, I'm only dedicating this single lecture to it, but it turns out I also offer an entire course on this specific topic, deriving optimal statistical procedures, information theoretical optimal statistical procedures. I have a course on that. So basically, this is a topic that's very important in for both statistics and machine learning, and of course for information theory. And it brings out the application of information theory to statistics. Okay, so we have already seen we have studied hypothesis testing problems quite a bit, but now let's come back to the statistical estimation problem. Okay, so here is one example. I'll just illustrate this topic via an example, a very useful example. So consider these random variables x1 to xn. Okay, these are IID copies, so these are independent samples from the same distribution, from a Gaussian distribution with mean mu and covariance matrix I. Okay, so let's say these are independent samples from this distribution. Let me specify a dimension. So independent samples taking values in RD, so d-dimensional samples, and generated from this Gaussian distribution with mean mu and covariance matrix I. So this is called the spherically symmetric Gaussian distribution. Now this mean mu, which is some vector in d-dimensional, so this mu is in RD, is unknown. And our goal is to estimate this mu by looking at this x1 to xn. So that's what we want to do. We want to estimate mu using these samples xn. So you can think of an estimator mu hat. This mu hat looks at your samples. So the samples are all d-dimension and you look at n of them. So this is where the input of this estimator is. And the output of this estimator is this vector mu, which is again d-dimension. And we use the mean square error criterion. How good your estimate is will be determined by the mean square error criterion. So we want the performance of your estimator is expected value of mu minus mu hat, the L2 norm of this. Sorry, this guy, if you don't, this is our mean square error that we saw earlier. So this is some just I equal to 1 to d mu I, the true mu I, minus mu hat I square. So note that what is this expectation over? Where is the randomness here? The randomness here is in this mu hat. So let me be very specific here. This is so this mu hat is mu hat of xn, and we take square also, means squared error, and this expectation is the distribution you choose for this expectation is this Gaussian distribution with mean mu. So this xn are generated from that. You pass it through this. You use this estimator, and then you want to check this error. And you want this. You want to understand how fast this error can go to 0. Okay. Now, this mu can be anything. So the error that you would look for is max over all possible mu. Mu can be anything in RD. And you want the best possible estimator. So min over all your estimators mu hat. You want to understand what this quantity is. This is called estimation under the min-max error criterion. So it's minimum over your procedure, maximum over all possible values of the unknown parameter of this guy. Okay, and we would like to understand how large is this quantity. What are the parameters here? The parameters that determine this quantity. I'll call this some error star as a function of the dimension d and number of samples. So we want to understand how epsilon star d n behaves. Okay, how fast can error go to 0 as a function of d and n? Okay, so that's the goal here. That's the problem we are studying. All right. So let me give a baseline estimator. Actually, it's not it's a simple estimator, but it's quite powerful. And I think you can guess what that estimator is. It is the empirical estimation, empirical mean estimate. So what does it do? Your estimate mu hat, I'll just put E here for empirical, of xn, just takes the average value of the samples and declares it as the estimate. So how good is this estimate? Let's try to compute its mean square error. So expected value under mu of mu minus mu hat E of xn is summation I equal to 1 to d. You can take this expectation inside here. Expected value over mu of mu I. Sorry, I should use j here, okay, for sample index. I is for dimensions, j is for the sample number. Minus 1 by n summation j equal to 1 to n xj, and we look at the ith coordinate of the jth sample. So what is the distribution? So this particular quantity here doesn't depend on all the coordinates, it only depends on the ith coordinate. What is the distribution of this ith coordinate? This ith coordinate, these samples are again IID, but they're single dimensional Gaussian with mean mu I and variance 1. So this sample mean, this can be written as expected value over mu 1 by n summation j equal to 1 to n xji minus mu I whole square. Note that each mu ji has mean mu I. Okay, so this is actually the mean of these guys. So this term here is exactly equal to the variance, because this is the mean of these guys. It's the variance of 1 by n summation j equal to 1 to n xji. So what is the variance of sum of n IID copies of a random variable? That's equal to, so this 1 by n square comes out, because this 1 by n square comes out. And so sum of a variance of sum is sum of variances for independent random variables. So that's just variance of any one of them, say the first one, and which is 1. So this error here is just d. So each term is just 1 by n, d by n. Okay, so what have we shown? Let me zoom out. What we have shown is that the error for this empirical mean here is just d by n. We've given a scheme which has just d by n error. So the best error here must be less than equal to d by n, which empirical estimator attains. Now question, and this is what we want to answer. Can we do better than d by n, or is the empirical mean estimate optimal for this min-max cost? See, the optimality of an estimator will depend on what cost function we are working on and what paradigm we are looking at. For example, earlier for the hypothesis testing problem, we saw two different kind of formulation. One was this Bayesian formulation. Second was this Neyman-Pearson formulation. Uh, Similarly, for estimation, there are several different formulations. This min-max formulation, we are looking for the best estimator with low worst case error, worst case over the unknown parameter values. Okay, and we saw that empirical mean actually has this error, the worst case error as d by n. And the question is, can you do better? Okay. And to answer this question, we need to derive a lower bound on E star dn, and this is what information theory will help us provide. So how do we get this lower bound? Okay, so very good. So now we'll try to derive that lower bound. Can we do better? So yeah, so this is clear, I hope. Okay, right. So to derive this lower bound, we first notice that we start by using Markov inequality, turns out. So consider any estimator. Consider any estimator mu hat. And we are interested in deriving a lower bound for max over mu expected value under the distribution corresponding to mu, the Gaussian with mean mu and variance I, of mu minus mu hat of xn is square. In fact, this max over mu is greater than max over mu probability under mu, of course. So this notation here denotes that all the probabilities are computed with respect to Gaussian distribution with mean mu and variance I. Samples are IID from that. So this is greater than probability that this loss function here, this is our loss function that we're using, xn is greater than equal to delta square multiplied with delta square. So why is this true? Why? That's something you can think about right away. Of course, I'll answer this right away. But so why do you think this is true? This is just Markov's inequality used differently. This loss function is a non-negative random variable, and probability that it exceeds some quantity is less than its expected value of this quantity divided by this threshold here. So this holds for every delta, greater than 0. So we'll choose delta appropriately later. Okay, so this delta can be taken out. This is equal to delta square times this max. Now, instead of this max, what is done in these proofs typically is that you restrict to a smaller subset. So let's say some m choices of this mu1 to mu m. Okay, you max over all mu in RD. This is all mu in RD. This is all mu in RD. Okay, and this guy here is max over all mu in a smaller subset. All mu in S. Okay. Where S is some mu1 to mu m that we will choose. So we get to design this mu1 to mu m to derive a great lower bound. and any mu1 to mu m is admissible here. And then this m, you can choose as large m as possible, but all this m and delta must be balanced very carefully, and I'll come to that part later. Okay, designing this difficult case. What we are trying to come up with here is a difficult case which this estimator cannot resolve. So what is this? Now this is max of p mu of this probability of error. But in fact, a max is greater than average, and therefore I can do that average. I equal to 1 to m probability under mu I. This is max over these choices, so that's more than average. Mu I, probability that mu I minus the estimator's output exceeds delta square. So this thing looks familiar. This thing looks like some kind of probability of error, average probability of error. You have hypothesis mu I, and this mu hat comes out, and you are checking what is the probability with which mu hat is far from mu I. You can define a rule, a new test that I'll define the test here. So suppose you say that T of mu hat of xn equals to mu I if mu I minus mu hat xn is less than, I can remove the square root here, no problem, is less than, say delta. Okay, now there are various possibilities this can go wrong. What happens if you don't find any? Let's say we just declare 1, mu1 if none found. And what happens if you find multiple? Let's say we declare, if you find multiple, then again let's say we declare mu1. It's just some error thing. Or multiple found. So somehow I will only declare an answer when exactly 1 is found within this distance delta. So this test okay, will output some mu I, okay, and we want this quantity to behave just like probability of error for an Emery hypothesis testing problem. Okay, we want to do that. So let's look at it a bit geometrically. So these hypothesis mu i's are here: mu1, mu2, mu m. Now suppose that each of them is within a ball of radius 4 delta. This is something I know the answer. You can try to optimize this and come up with this. So I know the answer, so I'm setting it up front. Less than 4 delta. And the gap between any two of them is 2 delta. So this is an assumption about our construction. We get to construct this mu1 to mu m. Suppose 1. First condition is mu I2 is less than 4 delta for all I. And the second condition is mu I minus mu j 2 is greater than 2 delta for all I not equal to j. So since this is greater than 2 delta, what we can quickly check is that you cannot find 2 mu I mu j which are within distance delta, because then by triangular inequality distance between mu I and mu j will become less than 2 delta. Okay, so this case will not arise. There will be a unique mu I which is within distance delta of mu hat. So what happens is you draw samples and you find this mu hat. This mu hat is somewhere here. Procedure we are suggesting here in this test is look for the mu I that is closest to it, that is within a distance delta of it, and there will be exactly 1. Okay, if any, none or exactly 1. Okay, if you have none, then you, let's say, make an error. But if there is exactly 1, then you declare that. So when will an error occur? If the true mu I is not within that distance, that's when the error will occur. So this becomes exactly the probability of error. Okay. So this becomes an upper bound on probability of error. So this guy, with this rule, this guy here is basically delta square probability of error for this hypothesis testing problem on mu1 to mu m. You want to check which is the true parameter, and with uniform prior. And this is some notation that I'm using. Okay, so this is the probability of error. Now, for this probability of error, how do we derive a lower bound? So I'll just write it in another way. This is equal to delta square probability that j is not equal to j hat, where j is distributed uniformly over 1 to m, and given j, you see this xn given j is Gaussian with mean mu. So these are IID. IID Gaussian mu mu ji when j takes value small j. Okay, and j hat is this output of the test. J hat is the t of mu hat of x. So this thing is just the probability that j hat is not equal to j. Now, this is where information theory kicks in. We can lower bound this probability by Fano's inequality. So by Fano's inequality, the right side, too many mistakes. Exceeds 1 minus the mutual information between j and xn plus 1 by log of the number of hypotheses that you chose. So log m. Okay, so what is the combined bound here? So we started with this guy and we have this lower bound now. So what we have shown is that max over mu in RD, mu in this is greater than this. So let me write it down. Max over mu in RD expected value over mu of mu minus mu hat xn for any mu hat. We haven't made any assumption about mu hat is greater than this times delta square. This delta square is from here. Okay, so this is mutual information. Now, one more thing we'll do is we'll bound this mutual information in terms of capacity and information radius. We can bound it any way we want, but we'll bound it by capacity and information radius. So this guy here, the delta square I'll retain, exceeds 1 minus max over the input distribution on j, pj plus 1 by log m. And this is that capacity formula for which we know that this is 1 minus remember this bound min over q divergence on pxn given some value of j. That distribution on xn given some value of j is q is an output distribution on n-fold alphabet, max over x, divergence between p, should I say j, pj, divergence between px and given j equal to j and q. Okay, this is the bound for this quantity, plus 1 by log m delta square. And in fact, we can substitute this q to be some j prime. And so this is again, this is the, remember I gave a bound called the diameter bound. So this is max over j not equal to j prime. So what are these distributions? The first distribution here is Pn under with mean mu I, mu j. So the Gaussian with mean mu j and covariance unit matrix, and mean mu j prime. That's the bound I'm using by log n. Okay. Now this term here is 1 minus n times, because this is just divergence, it's additive for independent distributions. J not equal to j prime, divergence between p mu j prime plus 1 by log n delta square. Now furthermore, these two are due to Gaussian distributions with mean mu j and mu j prime. So this is some simple claim. You can check the divergence here, p mu j for the Gaussian case with unit covariance is exactly equal to half into norm of mu j minus mu j prime square. So it's the Euclidean distance square, half of Euclidean distance square for Gaussian case. This is some calculation that you have to verify. Yeah, so these are Gaussian and you have to check this. You have to take, remember this is divergence between continuous distribution, so you have to take ratio of densities and take expected value. I'm not doing this exercise, but you can do this. And we have assumed that any 2 points here are so we have assumed this, they are at most 4 delta, so 2 of them, so this is less than equal to, you can show, so a plus b square is less than a square plus b square, or 2a square plus 2b square, so you get 4 delta square. Okay, and so 4 delta square and then 2 terms, so 8 delta square. Okay, 8 delta square. Okay, so this bound, when we put it here, we get max over mu expected value mu minus under mu minus mu hat xn is greater than 1 minus 8 n delta square plus 1 by log m. Delta square. Okay. So this bound will hold, and this will hold for any delta n m such that holds for any delta and m such that we can find mu1 to mu m satisfying those properties 1 and 2. So what are these properties 1 and 2? All of them lie in a unit in a Euclidean ball of radius 4 delta, and any two are 2 delta apart. So such constructions are called packings. So everything is inside this unit ball of radius 4 delta. Inside this ball of radius 4 delta, Euclidean ball of radius 4 delta. And you want to put points inside this ball, and any 2 points should be at least 2 delta apart. What is the largest number of points that you can find? Note that as you increase m, this bound improves. So we would like to make m as large as possible. What is the largest m you can find? So one way to do it is to just proceed greedily. How do we proceed greedily? Take a point, take a single point here. So this kind of constructions, this construction of packings inside Euclidean ball, and in fact packing inside Hamming, also called Hamming ball, is something we'll revisit when we look at channel coding problem. But this is some very cute problem with very rich history. So you can try to think about it. So what is the volume of a Euclidean ball of radius 4 delta? Okay, so it's some constant which depends on dimension d. This is volume of a Euclidean ball in d dimension of radius r. What is this volume? This volume is cd, some constant which depends on d, r to the power d. So what we do is we take a point, any point, and then once we choose this point, we remove all the points at distance 2 delta from it, and then we choose the next point. Since we have removed all the points in this distance, the next point has to be, this is the next point that we choose, say here. The next point that we choose is outside this ball, so it has distance more than 2 delta. We keep on doing this greedily until we cannot find any more points. So every time we find a point, we remove volume of this much, a ball of this radius. So what is the maximum number of points? How many points can we find? Well, that's the number of points m that we find by this method. This is sometimes also called the Gilbert-Varshimov construction for some reasons, at least for Hamming ball. But yeah, but this is a very simple greedy approach to find these points. Okay, so the number of points that you will find, m, is more than the volume of the bigger ball divided by the volume of the smaller ball. So volume of the bigger ball is cd 4 delta to the power d. The volume of the smaller ball is cd 2 delta to the power d. So this is 2 to the power d. These are rough calculations. Okay, so you can find these many points. Actually, not rough, but you need to argue these things. Okay, so we can find log m exceeding d. So you can find these many points actually. 2 to the power d. So when you take log, you get d. And when we substitute this here, we get max over mu, expected value over mu minus mu hat xn is greater than 1 minus 8 n delta square by d plus 1 by plus 1. Actually, this plus 1 by d is fine. Delta square, and we can choose any delta we want now in delta less than 1, and the optimal choice of delta roughly is when this becomes a constant. Let's say we try to make it half, so you can show that, but set delta equal to half, delta equal to so we set delta such that 8 n delta square by d plus 1 by d equals to half. So this happens if, maybe this itself is half. Let's do this itself is half. This happens if and only if delta is so this happens if delta square is d by 8n. Okay, so for this choice of delta square equal to d by 8n, so delta equal to root d by 8n. This bound here evaluates to, this is half, so you have half minus 1 by d by 8n. Okay, and for d greater than 1, d greater than 4, this is greater than d by 230, d by 32n. If d is greater than equal to 4. So very interesting, this bound holds no matter what mu hat you have, and therefore it holds also for the minimizing mu hat. So for the minimizing mu hat here, min over mu hat, max over mu, that's the quantity we were after, mu minus mu hat xn. We earlier saw that this guy was less than d by n, and now we are claiming that this is greater than d by 32n, if of course if d is greater than 4, but that's fine, we're looking at the large dimension case here. So we have a very tight handle on this, just tight up to some small constant. Yeah. Okay, so you roughly, if you want to make this error smaller than let's say 1 by 10,000, you need roughly 10,000. You need roughly 10,000 d samples. Okay, so these such bounds are called min-max lower bound. So I'll just quickly review what we did here in this min-max bound. So what we did was we first replace this expected cost with some probability of error cost, which comes in terms of the loss function being large. Then we chose a very we chose some set mu1 to mu_m, and instead of max over all mu, we look at this mu1 to mu_m, and we notice that the maximum cost over this set, maximum loss over this set of parameters, can be bounded in terms of some average probability of error. We have to construct these parameters carefully. Okay? These are two conditions which we came up with. And therefore, because now we have probability of error for Emery hypothesis testing problem entering the picture, therefore, now we can use Fano's inequality to control this probability of error, which we did. We used some bound, and we used some further bound mutual information, and we got tight bound. This is the whole idea. One interesting thing to note is that what we are saying here is that the bottleneck for estimation comes from Emery hypothesis testing. So you had, this is my picture of RD. Of course, RD is much bigger than this. It's also not two-dimensional. So RD is much bigger than this. Okay. So this is my picture of RD, and what the parameter can be anywhere here. But instead of solving it for RD, what we said was, let's look at a smaller part of it, which is where this mu was. This is that ball of radius 4 delta square that we have chosen. And remember, delta square that we said at the end was d by 8n. So this is the ball of radius d by 2n. Four delta or 4 delta square. Oh, I see. I may have made some small mistakes in calculations here. Okay. Okay, but roughly square root of this. This is the radius which we choose. This is rough. Some constant is here. And inside this ball, we found this as large number of points. And what we are saying is that a bottleneck in estimation is the ability to distinguish between these very dense points in a small neighborhood of 0. And from that bottleneck, we were able to derive a lower bound for min-max loss. So unless the number of samples is large enough, you cannot distinguish between these points, and that gives you a bottleneck on your min-max loss. And in deriving the lower bound for the hypothesis testing problem, the Emery hypothesis testing problem, we take recourse to this Fano's inequality. Okay, this method is called Fano's method for min-max lower bounds, and it's used quite widely, especially for high-dimensional estimation problems. Okay, so this concludes Unit 8. We have seen different kind of lower bounds. We have seen a lower bound for uh, source coding using Farnose inequality. We have seen a lower bound for Stein's lemma using data processing inequality. We have seen lower bound for randomness generation using just continuity of entropy. We have seen strong converse lower bounds, two different kind of lower bounds. And finally, we saw this lower bound for statistical estimation, for the min-max statistical estimation, which uses Farnose inequality. And they are all used. These are all of these lower bounds. What I've collected in this unit is different techniques for showing lower bounds. And in practice, many variants of these methods, separately or combined, are used. Uh, so we are done with sort of the bulk of this course. Okay, the way I have organized it, except that I have not covered the topic which everyone covers in this course yet. Okay, so what we have seen is we have seen flavors of many different kind of problems introducing these quantities: entropy, mutual information, divergence, and then we have seen their properties, and finally we saw how we can show lower bounds, fundamental lower bounds in information theory for some of these problems. And now what I'll do in the remaining part of the course is something that is traditionally done in this course, has to be done. That's a core topic in information theory. I'll do two very specific applications where information theory has enjoyed great success. I guess these applications are the first one where information theory did well because Shannon himself looked at these applications. He was motivated by these applications to come up with information theory. These applications are the compression problem. We have seen one instance of it as source coding theorem, but now we want to look at a more general uh, family of compression problems, different kind of compression problems. We'll also look at some algorithms like Huffman coding and arithmetic coding. So we look at the compression problem. And next thing we'll look at is the error correction problem, the channel coding problem, which is the which is the code design problem for communication systems. Okay, we'll look at these two applications in detail now. The reason I covered this general picture before these two applications is that since Shannon invented information theory, its applications have gone beyond just these two things, these motivating applications for him. It is now applied in a variety of areas, including computer science, uh, to derive circuit complexity, lower bounds, for example, uh, statistics, physics, and many areas. And so, what we were seeing till now in this course was not tied to any specific application as such and is of broader interest. But for the remaining part of the course, we'll look at specific applications. In the next unit, which I'll start with in the next lecture, I will consider compression problems. Okay, so see you in the next.